Thank you. Thank you for organizing this nice meeting. Thank you all for coming. As Rachel said, we'll talk about ACE potentials. What we'll do is I'll take about 20 minutes to half an hour to explain what ACE actually is. And I won't go into too many details, just try and give sort of a high-level introduction to it. And I'll focus on potentials, but maybe the main takeaway from this introduction would be that ACE really is sort of a general framework to build models. It's not one specific model, and sort of the general ideas that come out of what we now call ACE are going into many other places as well. And after we're done, maybe if there is time, Chuck will tell you a little bit about where the actual state of the art is now. What we thought is, before I give that theoretical introduction, anybody who wants to follow along for the tutorial that Chuck's going to go through, you might want to try and install that while I talk, so that there's no delay afterwards. So if you can follow me here, or actually hang on. So you probably want to start by opening this web page, acepotentials.jl. And the instructions that I have here on that slide are also at the bottom of the README on that page. So once everybody's opened that, I'll then go through the first few steps of that in the terminal, so you see what you should be seeing.
Maybe I'll just interject briefly. For those of you who installed Julia for the first time yesterday, you might remember we used a system called Julia Up. And if you just did the default things, you got 1.11. So they're recommending 1.10 here. And you can do that with you should be able to do that with just in your terminal, Julia Up add 1.10. You can look up the docs page for that if you have any issues getting that running. But that should be enough to just get you that. And then you can, I forget actually the syntax off the top of my head for how to launch a non-default version. So maybe just check the Julia Up docs.
Plus 1.10.
Ah, perfect. Plus 1.10. There we go. Easy as that.
For all I know, it might well work on 1.11. I've just never tried. So if you're very brave, tell me how it went. But if you want things to work, maybe use 1.10. Okay.
And let's also just go, because we have plenty of time. Let's go a little slow and make sure anyone who needs help with that actually gets the help now. So that
Absolutely.
Yeah.
Is there anyone who wants sort of more personal help?
So start just by creating a new project folder. In that folder, start a Julia project. Obviously, you start Julia however you start Julia on your machine. I just have a shortcut so I know which version of Julia I'm using. At that point, if you haven't used anything ACE related yet, you need to add the registry, which I've already done. Let me see if I can. You can just copy paste it from the README. That's probably better than what I'm doing here. Once you've added the registry, add ACE potentials. And that should then install. That part we've never had a problem with. So I'll wait a minute till.
Yeah, and if anyone wants help with this part also, just raise your hand and I'll come around. Yeah, it'll take a minute.
Anybody stuck here? Raise your hand. Anybody else?
I just added and then normally yeah. Just go ahead and try.
In package mode. So that's what this square bracket means.
So try it as
No.
Here are people who know what they're doing.
the thing that you need is the registry. So if you go back to that, what's it?
And everything is starting now?
And now it's just like
Or you still on Julia 110?
yeah.
Hopefully that will. I don't think it's the registry. Can we just copy the link?
If you want to use the development version,
Any help needed here, or you good?
it's just this is the sort of one.
What does one clone? Or
You don't clone anything.
you don't need to clone.
No, so you simply open a shell. You can also just follow and watch.
That pisses me off too.
Sorry about that.
It's a good question.
The amount of times I've run off, I should make a shortcut in that.
Yes, correct. That skill.
So if you open a browser, search for acepotentials.jl.
Maybe I'll also just say briefly, since we didn't explicitly talk about this yesterday, this registry add thing might be new to folks. Essentially, normally if you just do add without specifying anything, that's gonna go to the Julia general registry, which is kind of the general one, I guess. But there is a possibility to create your own package registry, which there's various reasons you might wanna do that, and so they've done that in this case. And so it's if you've used Conda, think about it like a channel, basically. So you're sort of adding a new channel, and that will give you access to this particular package, which is registered in this different registry. So that's all that's happening with this registry add, because we didn't talk about that yesterday.
Okay.
You wanna explain your motivation for having a suite registry?
Sure. That's many years old. That's the motivation before registering things in general became easier. It's as simple as that, and I haven't caught up moving all packages into the general registry. But back then it was actually quite a pain sometimes. Everything had to be merged manually, and you might wait a long time. And it takes you 5 seconds to do it in your own registry.
Oh, yeah.
And nobody checks that you actually put all the tests in your general registry.
Or that you're following the naming rules, or that you, what else is, I forget all the things now.
So, given enough pressure, I will move it into general registry and just need that pressure. So far, it hasn't been forthcoming. Yeah. Okay. So if you fall behind on this now, it is all on the README. It should be quite straightforward. But basically, once you've done that, you import ACE potentials. On a first install, I don't know how long this will take. It shouldn't take too long. And then what we did is we created a little function in here that actually installs the tutorials for you locally. So there are, for those who know what that is, that there are 2 literate scripts in the ACE potentials repository that get copied to your local folder and converted to Jupyter notebooks. Then I don't like the Julia way to start Jupyter, so I do it from the shell. Now we have a Jupyter notebook here, and there are 2 tutorials in here. And the first one is going to be the ACE potentials tutorial, and then the second one we're going to afterwards is ACE plus atom space tutorial. Okay, so once you have that up, I strongly recommend to click through the first few cells so that all the additional dependencies get installed and imported, because that can take a little while the first time you do it. Ignore that error, that's on my machine, you won't have that. That's because I installed some random registry that no longer exists.
I thought I would try being a guinea pig and do it in 1.11, and I don't know if this is a 1.11 related error, but I'm getting a bunch of things about revise. Do I need to have revise in this environment or something?
I have never used revise in my entire life.
Okay, so that might, I might have revise in my startup.jl, that might be the problem.
Yeah, it's on 1.11 for wise.
But then things seem to run okay? Oh, 11, it does. Okay, wonderful.
Okay, so that's probably a me problem.
Yeah, so basically I suggest that you click through all the way until this cell here where all the main packages are getting imported. Because after that, things will run more smoothly, and the rest should go quick. Yeah. Okay. Would this be a good moment to are happy to
So are you going on? There's one example of a really conversion today, which I've never seen. We don't have to necessarily.
Ah, okay.
I can send it. Let's try the copy.
This is an old version. There's some older version. No, because it failed, it didn't copy the second. Yeah, I should say I only ever tested this on Mac, and you did it on Linux. So okay, so we have several systems where it's been compiled as well on Windows.
Well, Linux.
We essentially never test on Windows.
It's probably okay for you to go ahead and
So I'll start giving a bit of a theoretical overview over ACE, and so maybe the first message to take away from this is that ACE really is a way to parameterize many-body interaction efficiently, and many-body interaction you get at all scales, and so basically we use it as a tool to parameterize ways to coarse grain across these scales, right? So for example, the one we'll be focusing on is molecular dynamics. That's the focus of the workshop in a way. That's the focus of that's been the original idea for ACE, and still the main use case is where you have the situation you want to run molecular dynamics simulation. You have potential energy that you need for that. Where does that come from? Well, you might use some empirical force field, like what Joe's been showing in his tutorial, but you might actually prefer to use an ab initio method, like the previous tutorial, right? But you have simulations where you simply cannot because of the computational cost, so you ask, can I just produce a surrogate for that? Right? So at the end of the day, the original idea for ACE was, can we approximate some ab initio potential energy by something cheaper, but ideally systematically to within arbitrary high accuracy. That's the goal. In a way, sort of conceptually, this has been done for many decades, right? So in the past, maybe in very simple ways. Let's say you want to simulate silicon, right? Sillinger-Weber potential is a potential of this form. You now have two potentials, a pair potential and three-body potential. Where should that come from? Well, one way is you can guess something. Another way is you can just parameterize it. So then you have two functions that you have to parameterize, and then you can run these simulations. And what's changed, really, the main difference now is that we do exactly the same thing, except we now go to much more general functional forms that allows, in principle, in practice is a completely different question, but in principle to construct potential energies that approximate whatever target you might have, be it DFT or coupled cluster, whatever you like, to within arbitrary accuracy. That's the dream, right? In practice, there are infinitely many pitfalls with how this can go wrong. Okay, so why do we care about that? This is now an old picture, actually, probably 7-8 years old, that I quite like to show. So what you see here is on the x-axis a number of properties of silicon. It doesn't matter so much what they are. On the y-axis, various different potential energy models, and that axis here, the arrows. And basically what you can see is that each of these potential energy models get you some accuracy, some properties to very good accuracy, and then many properties to even very poor accuracy. But an embedded potential, one of these universal approximator type potentials, can get pretty much all of them, for the simple reason that, let's say it doesn't get one. This is some surface energy accurately. You just add data, you just make the model a little bit richer, and then you will capture that too. So you can basically make your models arbitrarily rich and arbitrarily accurate, and transferable. That's really the okay. And then once you have these models, you now have not cheap surrogates in the sense of empirical traditional potentials, but much cheaper than ab initio methods, and you can then run large-scale simulations with them. given enough computing resources. And there are still many problems out of reach for these new models, but there are many more problems that can now be tackled. That won't be the purpose of this. Okay, so what's the, now back to really ACE. So how are these ACE potentials constructed? And I'll give you a perspective on that is, there are many different ways you can get to ACE potentials. People have 5 years later, let's put it this way, I now present this very differently than I would have 5 years ago. And along the way, I'll develop a little bit of history and maybe a few warnings on what things to think about if you think about ML potentials in general, because ACE really is just one out of an enormous zoo of ML potentials. That's another thing to Okay, so the goal is you want large-scale simulations. Right? Otherwise, if you only care about a handful of atoms, you can use DFT for the most part. And so the first step you need for that is you need some sort of scaling. You need some sort of a size extensivity. And the way you get that, and it's sort of in hindsight, this looks completely obvious, but it actually took 10, 15 years before people realized that was the right way to parameterize ML potentials. Instead of parameterizing the total potential, you parameterize a site potential. So you decompose total energy into contributions from individual atomic sites. What this means is, for every atom in the system, you look at the atomic environment, you say the energy associated with that site depends on all the atoms within the environment, and that in some way that I will not specify, but I will learn. Right? So this is the site potential which is being parameterized. Okay, so how will I learn that? Well, I just collect small structures. That's the key thing now. These site potentials, you can in principle determine them by showing them not large simulation domains, but small training domains, small structures that already capture sort of the full complexity, the full geometry that the site potential can see. So for example, if you look at this animation down here, that is actually the training set for the ML potential I showed in the previous slide. So many small snapshots fully determine your site potential. That is not a true statement in the sense of mathematics. That's an intuition, I should say, right? That has actually never been rigorously verified at any point for the mathematicians in the room. All right. So then basically what you then do is on these small snapshots, you can use something like DFT to collect training data. You write down a loss function, you minimize the loss, and that gives you your ML model. That's the overarching idea. So now how do you build these site energies? That's the question. And then the people in the room who understand chemistry, and they'll say, okay, but this cannot always be true. I can think of many scenarios where this will fail, and that is true. But basically, the ideas can be extended in very natural ways. Just I won't cover that now. Okay, so if you think of ML, you think of neural networks, right? So the first idea you have is, well, okay, I'm just going to stick in I take my atom positions in my atomic environment and I stick them in a neural network, right? And am I done? And so the problem is that with doing that is that inputs of atomic environments, they're sets, right? So you could have 3 neighbors or 5 neighbors or 30 neighbors. So any possible atomic environment must be allowed as an input. And so the first step you do is you create an input layer in between, right? So a descriptor vector, basically. You first map the atomic environment information into a vector of features of the atomic environment. Right? Okay, fair enough. You can do this. Not a big problem. The next issue you find is, well, I would like my model to be exactly invariant under all the symmetries I have in the system, in particular the permutation of like atoms. But this is easy. What's hard is the rotation and reflection invariance. Right? So you can do that. Basically, if I rotate the atomic environment like here, the energies have to remain the same. And so this leads to some interesting questions. And I think sort of the first big steps were made by these 2 papers here. And in essence, what they did is the following. They used what's called, I'm saying in essence because in practice how it's actually implemented in these 2 is different. But it's basically essentially they use what's called the power spectrum of the atomic environment. What you do is you embed the particles. So you know these are the vectorial the vector distances to the neighbors. These are the radial distances. Through a pooling operation, you generate a permutation invariant descriptor of the atomic environment, and then you take symmetry adapted correlations of this in order to make sure that this descriptor vector becomes really invariant under rotations. Don't worry if that's not obvious to you why this is happening. If you're interested in the theoretical details, just chat to me afterwards, and I'm very happy to talk about this as long as you want. The issue that it then turned out that these kind of feature vectors are actually incomplete. In the following sense, you can easily, I don't know, in hindsight easily, find pairs of atomic environments that map to the same descriptor vector, but these atomic environments are not the same up to symmetries. And so what that shows is that these models, these ML models you constructed this way are not actually universal. They cannot possibly approximate every possible potential energy. Okay, so the obvious next idea is, well, we just add more features, right? You can add, for example, instead of the power spectrum, you can add the bispectrum. So power spectrum, you can think of symmetry adapted 2 correlations, bispectrum symmetry adapted 3 correlations. Turns out this is also incomplete. Again, you can find examples that this doesn't fully describe the geometry. You can go to n correlations. Nothing is known about that. But the key next idea here is the key concept is that when you keep adding more and more complexity to your descriptor, to your feature vector, you give the feature vector more and more information, eventually it becomes so rich that you don't even need nonlinear models anymore. Yeah. So basically what ACE is, it says take n correlations of your atomic environment, n-fold tensor products, symmetrize them, and then make a linear model out of it. That is one way how you can call it an ACE model, and I'll show you a second way in a second how you can interpret this. You find some way to take atomic environments, you embed them into vector space, you take n-fold tensor products and symmetrize. And the linear model out of that is an ACE model, if you wish. Nowadays I prefer to write this differently because I just find it much easier to think about this. You can equivalently say I take a tensor product of this rank 1, n-dimensional rank 1 tensor with a parameter tensor subject to a constraint. And it just makes a lot of things easier to think about, and so this is how I'll continue to write it from here on. Okay, so this is now the summary. This is now pretty much that is what you need to know if you want to implement this. Right? It is at the end of the day quite a simple procedure. Again, you need to embed the atomic environment, right? For that you embed these neighbor distance vectors, the angular component using spherical harmonics, the radial component using whatever radial basis you think is a good one. And then you perform a pooling operation. You take n correlations and inner product with the parameter tensor, and then you're summing over the sides, and that is an ACE potential already. Okay. So when written like that, it looks quite simple. The devil, as always, is in the details, but it is actually not hard to get started, even from scratch, in principle. So now, why is it called atomic cluster expansion? The reason is this. The first person who sort of derived the ideas were floating around in many ways, but the first person to just put all of this together was Ralph Kautz, and he actually started from something else. It's still not quite exactly how he formulated it, but for the sake of simplicity. So he actually started from a many-body expansion. And it turns out that if you start from many-body expansion and then you take a tensor product expansion of these n-body potentials, and you reorganize the algebra a little bit, you end up with exactly the same thing. So basically, each of these entries in the parameter tensor can be interpreted as a parameter of these n-body potentials. There's sort of this very clear connection between the two. And that's why this method, it has this sort of additional feature of being very nicely interpretable. You can really, you can identify very nicely what each parameter does in your model. What else should I say at this point? So you have this sort of chemical or physical interpretability. The next thing to observe here is the cost, right? So you get linear scaling in the total number of atoms because of the spatial composition of total energy. You get linear scaling in the atomic environment size, right? So if I have 30 or 100 atoms, the cost of assembling this grows linearly. And then you have whatever scaling comes here out of the cost of this tensor product. And so these are the things one has to think about when you actually implement implement this method. So basically, how should I choose these different parameters now? And I guess there's a fair amount of empirical work, theoretical work, and exploration that has gone into doing that over the past few years. How much more do I want to say here? Let me stop here for a second, see if you have questions, and then I might show 2 or 3 examples, and then we can go to the tutorial.
So you mentioned that one advantage of having a rich representation is you don't need nonlinear models. Is that for speed? Is the slow bit the nonlinearity, or does the representation get so rich that it's actually slow to compute?
Very good question. I meant to talk about it and forgot, so thank you for the cue. So the way I've written it, it is a linear model, but I can pick whatever tensor format I want. And if I choose, for example, a Tucker format for this parameter tensor theta, I get a highly nonlinear model. And so, for example, so our code can in principle support such formats. The tutorial is going to be purely for linear models, because then you can do the parameter estimation in 2 minutes or even less. But so, for example, like earlier we were chatting about the code that Ralf Traut's group wrote, and his group, they use a Tucker format for that tensor, and what that allows you to do then is use basically fewer embedding, fewer features. It sort of compresses the whole model a little bit. And that it's harder, it's more expensive to estimate the model, but then you get a smaller model in the end that is cheaper to evaluate. Where exactly is the sweet spot here? I don't know. How many of you don't know about tensor networks? A little bit, right? So it's an enormous model design space. I would love to know what the optimal choices here are. And what makes this particularly interesting is you can't just use arbitrary tensor formats. You need tensor formats that maintain your Lie group symmetries. Yeah.
Can I add one more thing? So you showed some examples earlier of configurations of atoms that are actually quite chemically different, but yield the same descriptor when you extend only to low order. And so the older, the sort of original machine learning potentials use low order descriptors and typically put them into a nonlinear model. But no matter how fancy the nonlinear model would be, you wouldn't be able to distinguish these pathological cases. And so even if you might not use the most rich base descriptor that you like, you have confidence that you can turn the knob high enough to at least be able to distinguish the most pathological cases.
So the paradigm examples are the Bela-Parinello networks and gap-SOAP. That doesn't mean those are bad models. They are very good models for many, many problems. It just means they're limited. There's a theoretical limitation to what you can do with them. Yeah. But if there's a concrete problem you want to solve and Bela-Parinello network do the job for you, they're probably easier to use than any other ML potential on the market these days. Yeah.
For completeness, like, is it that you need to go to like infinite tensor correlate or infinite correlation, or what's the?
You just know that you can keep going to higher orders.
Because I thought they proved completeness in one of those papers, and I.
That was quite different. They changed the framework.
Oh, okay.
And so it was a bit of a cheat, actually, I would say. They changed the question.
Okay.
It was an interesting observation. So basically, if you go to three body features and then you may have to make the features learnable, then you can get. But then you get into deep sets.
Yeah, I don't know what
I
that is.
suspect there is in here that I haven't. Yeah. Anyways.
Sure we don't know, but if we go to correlation order n, where n is the number of papers or something.
Sure, then we're done, for certain. I think in fact n-1 I can prove.
Yeah.
I'm not sure that's helpful.
It's helpful for these sort of like proving things.
But the reality is that we have yet to encounter situations where going beyond n equals 5, 6, 7 helps you in any way. More realistically, we're in the range of n equals 3 or 4. Okay. Anyways, there are many hyperparameters that one has to pick. Part of what we tried to do with this ACE potentials code that the tutorials are on is to automate this as much as possible. So this is what a typical model construction looks like. I have a data set that is a training data set that contains titanium aluminum structures. Okay, so I have to tell my model that it will see titanium and aluminum. I give it the correlation order. Total degree is a way to measure how large the model should be, how many basis functions, how many features it should use, and the cutoff radius. But in fact, none of that's really needed, right? So at the moment, you still kind of have to specify these things, not the cutoff, that's automated by now. But some of these things are easy to get rid of, and we should get rid of as soon as somebody finds the time to do it.
How are you automating the cutoff?
So the cutoff, we basically use a heuristic that you take, is it Van der Waals radius? It's one of those radii, atomic radii, and then times some factor that empirically over the past 10 years turned out to be a good factor.
Okay.
And we make it a bit conservative, so make the cutoff a little bit larger than it needs to be. So that means you increase the cost a bit. And so if you want to really optimize and get better performance out, then you try and squish the cutoff back down a bit. Okay, so I said I wanted to show a few things. Let me maybe not do too much, but so for example, this example I showed, okay, so you can do this. This was done with GAP in 2018. Then I think two years later or so, we did this with ACE. We essentially matched gap accuracy, and the cost improvement was, I think, pretty dramatic, factor 30 or something like that. So these potentials are reasonably fast, and but there are fast potentials. This is something that maybe people would find interesting because these ACE potentials are linear potentials. You get relatively good uncertainties because you can apply. For linear potentials, it's very easy to put to estimate parameters in a Bayesian framework. That means, and once you have these uncertainties that come out of the Bayesian parameter estimation, you can do quite effective active learning. Right? So for example, this Christoph Ortner is a PhD student in Cambridge, Gabachani's group, and he developed this active learning protocol where he could then produce phase diagrams. So very, very small models that are very, very cheap to evaluate. Produce phase diagrams for solid-solid and solid-liquid phase transitions. But people have used this for a number of things. Here are just a few pictures to look at. No other reason to show it. So in principle, the framework is flexible, relatively easy to use, I would say. At least I hope so. You can tell me otherwise afterwards. And yeah, maybe the last thing to say is it's also kind of out of date. Right? So it's only 3 years old now, what were the things I've shown you, and it's probably 10 or 20 years out of date now. That's how fast the field is moving. So my personal interest in this is actually mostly theoretical. Rachel said, potentials and beyond. This is what I'm trying to show here. I've quite enjoyed exploring how one can use the same framework in many other scenarios. This is just a list of examples. I won't go through it, so we don't waste too much time. You can get to the tutorial. But these are all things that I'd love to chat to people about who are interested. Basically all the way from coarse-grained molecular dynamics down to elementary particle physics. There's nothing you couldn't try to do. It's that generic. All right. So yes, but how hard is
I don't know what
gravity? I just don't know enough about it. Anybody interested in gravitational stuff?
Two volumes should be enough.
Huh?
You should be exposed to two volumes.
Well, so that's what I don't know, right? So but because you have to coarse grain it in order, if you want to simulate the entire universe. No. Then you need two body. Then there's no. We don't need to do anything. Right? Anyways, let's stop it here. We can come back to this. But let's now focus on the tutorial. This was really just sort of to show a little bit what can be done, what the background is, what the framework is, and Jacques will show you now how this looks like in almost in practice, right? And then afterwards, we can talk a bit about how it connects with the atom space ecosystem.
Does anyone else need tech help before we get started? And for them, including on 111.
You? As you wish, whatever you. Is the font big enough? Should we make it bigger?
Bigger is better.
Do one more. Then I think it gets sorry. Command. Control is command. Even though there's a control. I don't know who thought that up.
Okay. We're going to start with this longer ACE potentials tutorial. This should be very fast, but I'm going to go ahead and run the first setup block.
Yeah, I also only ended up with one notebook. That was a comment that,
A comment in the Zoom, or?
yeah.
Yeah, Nicholas said, copy tutorials only downloads one notebook, is that right? I ended up with two, I think.
Yeah, I've seen one from someone on Windows. For some reason, the Windows
I
conversion.
don't think it's, I have a Mac.
Yeah.
Yeah,
I got two.
you got two.
Well, did you get this one at least? The ACE
I did get
potentials?
this one, yeah. No, this is the one I have, but
We can start with this one.
yeah. It's gonna be.
So did you learn yesterday, I'm sure you learned all about the package manager, did you learn about the status command? Raise your hand if you know this command. I'm just gonna force you to be interactive. All right. Thank you, Joe, enthusiastic. So this just tells us that we've installed a few packages, including most importantly,
Gotcha.
right now, this ACE Potentials v8.4 package. So we'll go ahead and load a few more things before we get started. So machine learning potentials require data, and the data is most often first principles calculation, so DFT, density functional theory, more than anything else. And we typically organize our data into data sets. So we have a kind of small but hopefully growing collection of data sets that you can just download and start experimenting with. And so this command just lists the ones that are available now. So we'll go ahead and use this example dataset command to load what I'm going to call the tiny silicon dataset. So going through this notebook, we're going to work with two different silicon data sets, and this first one is the tiny one. And then next we will download an external data set, which is the sort of full, larger data set. So we use this notebook sometimes to introduce example Julia commands. And so this block tells you how to learn a few Julia commands for downloading files or loading files, including with this XYZ package. So we're loading the data set from an XYZ file. So I said we have two data sets. The tiny one has 53 structures. The large data set has 2,400 and so structures. I neglected to say that these are the silicon calculations that were run as part of this kind of landmark 2018 general purpose interatomic potential for silicon, one of the early gap potential success stories. Okay, yes?
So, in data set, there's a lot of atoms, this object, so this atoms is the type inside the A3 or is we should present this one with atoms?
So are they julep atoms still, or?
No, julip's gone now. So if you see julep atoms.
No, he's just asking what they are now. What
is this type is atoms? If we want.
Oh no, this is actually James Kermore's implementation of atom space. It's XYZ. That's the package that loads these structures, and so atoms is the type that XYZ defines to store structures. Like it's plural. Atoms, many atoms. It's basically a one-to-one copy of the format that ASE uses, implemented in Julia.
Similar, but not exactly the same. Okay, so let's start looking at these data sets a little more carefully. So I've run a few more Julia commands that you can dig into if you're new to Julia and want to understand, but we can see from the results that in the tiny data set, there are 4 config types, which just means some particular geometry or structure type. So we have the isolated atom, we have 25 examples from diamond silicon, ground state of silicon, 2 examples from a bigger liquid cell, and then a few examples from another competitive crystal structure, beta tin. But then in the full data set, we have much more diversity, lots of things, some surfaces, some cracks, lots of crystal structures. SP2 is probably an amorphous. So moving on to more data set analysis, we're going to plot some radial distribution functions. Okay, so here's the radial distribution function for the tiny data set. What do you think this red or orange line is? Do we know what a radial distribution function is? Surely someone. So we have an x-coordinate that's in angstrom, so this is distance away from a central atom. And we have a histogram of kind of where the atoms are located in the data set. So what do you think this line is that corresponds to a peak? Yeah, it's kind of the nearest, sort of an average nearest neighbor. The line is the exact nearest neighbor distance for the cubic diamond ground state. And you can see that, so here's the second and third nearest neighbor, and you can see that the actual data tend to follow what we'd expect. And if we look at the same RDF plot for the full data set, we see a very similar looking picture, but everything is much smoother because we have more data and there's more averaging, and the plot just looks nicer. So we can also assess angular variation. So this is an angular distribution function that we're computing next. As before, we have a kind of rough first approximation coming from a tiny data set and then a smoother one down here. And we can see an expected peak at this 109.5, which is associated with that same diamond structure. A lot of the data, even though it's not all taken from diamond configurations, has a similar peak because that's how silicon atoms like to arrange themselves. Okay, so this is just for later use. We're going to make a function that extracts the energy, and in particular, the DFT, density functional theory energy, from each config in the data set. Now on to the ACE descriptors that Christoph introduced. So some of the important parameters when specifying an ACE model are the elements, what types of atoms do you have, what is the correlation order or body order that you, so how many types of interactions do you have, 2-body, 3-body, 4-body, and so on. Total degree, so we can think of these bases, at least if you use certain types of radial basis functions, as polynomials. So we use the total degree of that polynomial as a cutoff parameter. And the same thing is true for spherical harmonics. So spherical harmonics are polynomials in kind of the normalized vector pointing towards the atom. And a cutoff radius. Now we're going to go through and for each configuration, we'll step through the atoms one by one and compute the ACE descriptor for each site in a particular configuration and then average over the entire structure. So this gives us, for each structure in the data set, a set of ACE vectors. The vector is each individual atomic site representation, and then we average over all of the different sites. So since we have a vector, we've taken our configurations and we've mapped them to some kind of vector in a high dimensional space. We might naturally try to do some dimensionality reduction. So here, this is a relatively straightforward, simple principal component analysis for the structures computed on the tiny, for the ACE vectors computed for the structures on the tiny data set. And if you recall, we have 4 different config types. There was the isolated atom, which is way up here by itself. And we see that the diamond structures in this orange color do tend to show up next to each other in this PCA plot. The 2 liquid structures show up right on top of each other, but it's not as good at identifying all the beta 2 structures in one cluster. We'd have to maybe think more carefully about what dimensionality reduction tool we were using or other features before we could get everything nicely segregated. Now we'll just repeat that analysis on the full data set. Now you can see there's the full diversity of all kinds of surfaces and other things, and it's much harder to interpret this plot. But you do still see some segregation of the ACE descriptor contains information about the global structure, and then this dimensionality reduction is able to kind of start identifying which structures are which and put the structures that are similar close to each other in this space. That's sort of a classification task. We're just trying to understand what the structures we have are in our data set. Now we'll move on to model fitting. So I'm going to create an ACE model using the same parameters as before, except now I'll give a reference energy. So one thing that we find to be very good practice is to do all of our fitting relative to the energy of isolated atoms. So that's what this last parameter is, the isolated atom energy. And we'll go ahead and do a linear fit. So we have each structure, we have this ACE vector, and we have the target energies and target forces and target virial or stress terms, and put all of that together in this loss function that Christoph showed, and perform a linear fit with some regularization. And this is a relatively straightforward QR factorization-based linear fit with regularization. Nothing too fancy going on here. So the solver is outputting some information. At the end, we have error tables. So we have a relatively small data set, but also a relatively small model. And you can see the error, the RMSE in electron volts here, and then also separate errors broken out for the different config types, as well as the forces and the virial term.
And these energies are energies per atom, right? Usually.
Yeah, that's right. So what I was showing here was the error associated with the fit. So we're using the tiny data set as our training data set. Clearly, there's not that much diversity in the tiny data set, but we might ask how well the model trained on the tiny data set does if we apply it to the full data set. And that's what's shown in these test error tables. So there's lots of different structure types, but the main takeaway point is that the error associated with taking the model trained on the tiny data set and evaluating on the full data set is really quite large. So this 430 MeV per atom we're not going to be able to use this potential for very much. So you might want to use these potentials in LAMPS. We've made a bunch of changes to the back-end way models are constructed. Christoph and his team did a lot of that over the summer, and we still have to update our LAMPS export, but so we'll skip the LAMPS part. But we can still save and load the model from within Julia so that once we fix the LAMPS export, you can reload your model and export it to LAMPS.
So let me just make one comment about this. So if you want to use linear ACE models, there's actually no really strong reason to use the latest version of ACE potentials. Just use an older version, 0.6. It's in some regards better than the new one, actually. In some regards, no, maybe not, but and then you do have the LAMPS export, and then you can actually use the potentials from LAMPS. And in fact, almost everybody who we worked with wants to then use potentials in LAMPS. They don't particularly care about doing it any other way. Right? Is that fair? Something we hope to change, but so at the moment, that's really the
the hardcore material scientists who just want to run MD typically use LAMPS. Maybe not forever. Okay, so moving on to part 4. Any questions now on model fitting generally? This last part is a little more interesting. Okay. So, one advantage of the linear setting, you can also get this from other types of regression, but the linear setting allows us to achieve very easy kind of error bars in our uncertainty, so uncertainty estimates. And we can do that just by switching from a sort of standard linear regression setting to a Bayesian linear regression setting. So we'll go through and create a new model with slightly different parameters, and we're going to go ahead and fit it for a second time, trained on the tiny data set, importantly. And this time we're going to use the BLR solver. So before we used a QR solver, but the BLR solver is a Bayesian linear regression solver. And it's going to give us a committee. So now we get not just one linear model, but 30 linear models. And when we compute the energy for those 30 models, for example, or forces, there'll be some spread in the predictions because each member of this committee is drawn from the Bayesian posterior. So we have some understanding of how confident or not confident our model is when applied to a new configuration. So this solver is a little more complicated, so it outputs a little bit more, but in the end, we have a model just like before. So again, I'll remind you that we trained on the tiny data set, and we're going to want to assess the performance of the model on the full data set. So that's happening right now. Oh, I have to press the next. So just for remind you, the tiny data set had a handful, something like 40 structures, I forget, but the full data set had 2,400. Now we have taken that model trained on the tiny data set and evaluated it on the full data set, and here's a parity plot. So we have the true energy plotted against the model predicted energy. The plots in orange are the data that was used for training, and the blue dots are data that wasn't seen during training. And so we can see this section up here, for example, that is really poorly understood by the model, and you can see some error bars or sort of uncertainty expectations on those data points that are quite large. So clearly there is room to improve. The RMSE for the full data set is 500 MeV per atom. To update this number. So let's do something where we take from this plot 5 configurations, and we choose the ones where our model is the least confident. And we'll add those 5 configurations to the training set and refit. For those of you following along, how's the notebook working? Has it crashed?
First time I tried to run the fit, it seemed to just hang, but then I just restarted the kernel and everything worked fine, so I don't know.
All the way to the end, or?
Well, I'm just following, I'm up to the point where you are again. It seems fine.
And the QR part seems to take quite a while. Was that the part that you were?
Mine hung on the first fit, actually. It just never even started showing the output with the progress bar. It just hung for like probably 2 minutes before I gave up and killed the kernel. But then when I started it again, it was fine, so I don't know.
I think there's a step coming up soon that might stretch your machine's bounds. At least for now, we can look at this result. So just to remind you, we had all of this data up here. We took the 5 examples where our model was the least confident, retrained, and now all of a sudden, those examples snapped onto this line. We still have some uncertainty here, and the model is not doing perfectly, but we didn't have to add very much data to make progress. Let's go and do 4 more cycles. So we'll add 20 more structures in 4 sets of, 4 sets of 5. It'll take a little while. And if your machine, we think, doesn't have enough memory, this cell might give you some problems, but it's a little bit unpredictable, and we're still trying to understand this new backend. So it's a little bit bleeding edge.
So this is running on my laptop, so it
Yeah,
should in principle
not-
run on most modern machines. We haven't figured out yet what exactly where the performance bug is. So fingers crossed. Everybody has M1 or better, then you'll be fine.
What exactly is the new backend compared to, I guess, 0.6?
So I will answer as succinctly as I can, and then Christoph can correct me. But these things evolve with time, and it turned out that simple linear ACE model that was in the first and maybe even the second version of the package was great, but actually there are other things you'd like to do, for example, nonlinear fitting or other model types. And the new backend is much more generic and better.
Yep, that captures it. If you want to see the details, maybe after the tutorials.
So we're on to the third of the 4 refits. Yes.
So this new model is like a training from scratch or based on the previous one?
Oh, good question. Training from scratch. Yeah, but just with slightly more data.
It's not a fine tuning like you would be used to from foundation models, because it's all linear. You just
Yeah, another advantage of the linear setting is that the fits can be relatively fast. You can fit them into memory. Almost there. So is this cell working for you, Rachel?
Yeah, I made it through. I have my new parity plot.
So now we have, after adding our original 40 or so structures, I guess 50, and then adding 5 sequences of 5, we're up to 78 in total out of the 2,400 from the full data set. And yet, even though we haven't used very much of this data set, about 3%, we've still hit a model that does relatively well across the board. We could probably continue to refine and maybe drive this error down, but I think we'd probably have to make the model a bit bigger for that to happen. So, if you remember, we started with an RMSE on the full data set of something like 500, and then having added a few 20 or so configs, we're now down to 23. So what can you think about, or can you answer, this toy example is sort of pointing us towards something else that we might do that would be more useful in practice. Can you think of what that would be?
Active learning?
Yeah, why is this like active learning?
Well, in active learning, you're typically looking at your points with highest uncertainty and then seeking out more data in those regions and training in an iterative fashion.
Yeah, exactly. So, we have this bigger data set and we already have done all the DFT calculations for it. So we're using it as a sort of example. But you can imagine building a model that's fit on a small number of DFT calculations and starting an MD run, maybe, and monitoring the uncertainty, the model's confidence as the MD goes forward. And then maybe the MD trajectory wanders into some very unknown region. The model says, I'm really unconfident. We stop, we add that config to the data set. And hopefully with a minimal amount of DFT calculations, we can get to a robust model, yes.
Regarding the UQ, so I mean, looking at especially some of the earlier versions, it seems that the uncertainty is often quite a bit underestimating how big the actual errors are, but I guess for the purpose you're using this for, it's probably more important that they're just correlated with each other and it need not be like a perfectly calibrated uncertainty estimate, but rather, I forget the other, there's like sharpness, is it sharpness? Whichever one it is that basically says like the error should be, or the uncertainty should be larger when the error is larger, essentially. Have you tested that? Does that sort of hold up reasonably well? Because if it doesn't, then that's sort of a little problematic for this type of an active learning scheme, right?
Yeah, so completely agree. If I can reframe your question, you're almost saying, why don't these error bars cover the true?
Well, I mean, I would say what I'm saying is that that's maybe not even a problem if you're just gonna chase large uncertainty regions. Probably the thing you would care about more is actually, are the largest uncertainty ones also the ones that tend to have the largest errors?
I think what I can say is that the type of active learning that we described, where you just look for uncertain predictions and iteratively add to the training set, that seems to work very well in practice. But there's a lot still to be understood about how to sort of maybe rescale some of these uncertainties using conformal prediction or other things.
Can I add something here? So the way we're applying the Bayesian framework here and the way almost everybody does it is actually complete bogus. We're assuming that we have noisy data and then we ask how the noise propagates through the model. That is not what we have. We have data without noise.
Yeah.
But we haven't covered the whole space of possible things we want to predict.
Right.
So there's a huge leap of faith in all this, and I started talking to Yusuf about how to fix this. I know other people have other ideas how to fix it. But exactly what Chuck said. There's a lot to be understood here on how to get robust and reliable uncertainties. Because you don't just want to do active learning. You want to run a simulation and tell you the error is this. Right?
Yeah.
It better be in the right order of magnitude.
Right. For that purpose, yes, absolutely. But more for the active learning, actually, the quantitative part is
It seems to be all right. That's what we use it for.
Sure. Fair enough.
Another variant of that active learning that also seems to work in practice is that instead of just passively monitoring the uncertainty and then once the trajectory wanders into an uncertain region, grabbing that config, Cass van der Org and Christoph showed a slide with his face on it, actually uses that uncertainty to drive the trajectory to push the model into uncertain regions. And that also, while the uncertainties may not be perfectly calibrated, also seems to work relatively well. Okay, any questions, any further questions? So the rest of the notebook you can, you can look into. This part is relatively a sort of vanilla fit, but showing you the syntax for how to do multiple elements. So here, it's a aluminum titanium data set, and you can see the RDFs for titanium against titanium, titanium against aluminum, titanium or aluminum against aluminum. The syntax for fitting with multiple elements is slightly different. You give it 2 elements in this case instead of 1, but most of the rest proceeds as before. And we can fit to this data set just like we did before. I think this last part, part 6, so it shows you, for example, how to now do multi-threaded or multi-process fit in this case by adding more processes. You know, if your machine doesn't have your machine doesn't have 11 cores, you probably want to change this number. But you could use this section to reproduce some of the actual data that appears in the ACE potentials paper. So I'll maybe leave this for you to experiment with if you want. I can let it run at least. Hand it back to Christoph for notebook number 2. There's a few more tutorials and other examples in the documentation, which you're welcome to look at and ask questions. Okay. Right.
Anybody have questions on the first part?
If you add 10 more processes, does it make it 11 processes in total? Because you haven't.
Yes.
Yeah. So.
Yeah, it should have put 9 there.
And -1 for your machine.
So, something, is this like this potential like a correction for like a step more basic Leonard-Jones potential? So you're like doing everything.
If you had a data set that was composed of entirely Leonard-Jones calculations and you fit this potential to it, you would probably get the Leonard-Jones potential back out of it. But this potential also is more flexible in that it can include more than the 2-body Leonard-Jones interactions. And so if you gave it, so another classic potential is a Tursoff potential, which is often used for silicon. If you gave it some data that was a Tursoff potential that was derived from a Tursoff potential, you could probably recover that as well. And then as you have higher and higher many body effects, use the expansion and hopefully capture those too.
Okay.
So it is, I wouldn't exactly call it a correction to the Leonard-Jones because we don't program any Leonard-Jones in to sort out, but it includes the Leonard-Jones as one special case.
Okay. So in like your training data, if I like subtracted the energy of some other model, then like it would.
You could, if you did that in a pre-processing step, then you could think of it as a correction.
I think it sounds like a great idea to try. I think what people have found who did try that is that it makes the problem harder, not easier. Because when you subtract an empirical potential from DFT data, you're making the correction ends up often being harder to learn than the original. And that's because the empirical potentials themselves are often easy to learn. And it's the extra stuff that they don't have that are difficult. This is purely empirical. Yeah. So in specific scenarios, it might be a really good idea to do this. For example, you want the repulsion as atoms get close to get perfectly right. You might want to subtract the ZBL potential. And the difference between DFT and ZBL may well be a good thing. I'm not certain about this because DFT doesn't behave like ZBL as atoms get close, but it's the gist of it, the idea, right? So if you know there are sort of specific features in the potential, you could remove them. Specific difficult features.
Is that hold true for like Coulomb potential as well? Because that's gonna affect the cutoff you use here, and that is something where it's like actually physically the correct energy function, and not just an empirical.
Let's maybe give a simple example, dispersion correction. It's a lot of DFT codes add dispersion correction empirically on top. That is something, there's no reason to learn that. Just subtract it from the DFT data and then add it back onto your potential. Coulomb is a bit trickier. It depends now what level of Coulomb.
Screening and you don't know what charges.
So I'm a bit uncomfortable giving a generic answer to that. But in principle, you're right. Something like Coulomb, you might want to treat differently.
There's maybe one more question here. Good, well, we're around.
All right. So, the second tutorial, which
So here there's a
order, when you define the model, so this order and the equation is which?
Let me show you that here because we have to do this here anyways. So if you switch to the second tutorial, and then we can talk about your question in a second. Yeah? And then again as before, right? So install the extra packages, and then I'll So and then then load all the packages that are needed, and then we can get going. So the second tutorial is intended really just to show how ACE potentials interacts with atom space ecosystem, and basically it does as you hope it would, I think. So what did we? We had presentations on atom space, atoms calculators. So DFDK is implicitly directly relevant, but not.
Sorry, Christoph, someone on the chat is saying that the audio has gotten fuzzy. Maybe just like hit the mute and unmute on the little console there, and we'll see if that helps anything. Someone said the sound suddenly got fuzzy. I don't really know.
It's just my voice.
Well, your voice has been the same the whole time, and the complaint came only 1 minute ago. So
How's it going now?
let's see if they respond in the chat.
Oh, it says
Okay,
good. So
sounds
maybe
like-
just
Oh,
speak up.
okay. It must. Okay,
Oh.
Nicholas says it's fine, and then Hari Haran says, okay, it might just be an issue on their end. Okay, I'll just note in the chat that we are recording this, so hopefully they can catch up later.
So I'll start just by very quickly fitting a potential that we can use as an example, and so for no particular reason I decided to fit the copper potential. So you know, we have a few data sets easily accessible through ACE potentials just to play around with without any extra effort. So you can load an example data set like this. So I'm making an ACE model. ACE1 model basically means it's compatible with older versions of the ACE potentials package, hence ACE1. It's a linear ACE model that has the element, for the element copper only. Order 3 means correlation order 3, which means body order 4. And total degree just specifies how many basis functions you use, 20 for 2-body, total degree 16 for 3-body, total degree 12 for 4-body, and sort of this ramp down sort of suggests that we believe that the higher you go in body order, the smoother and the smaller the contributions become from the higher body order terms. Anyhow, so if we do this, we can then look at how big the model is. Here I didn't specify the cutoff radius, right? Because I said there are heuristics, so we might want to look at what that is. And so here for actually cutoff radius, that's already one of the, comes from a different package. That's from Atoms Calculators Utilities. That's a package that's built around Atoms Calculators to make it easier to implement certain classes of potentials, pair potentials, site potentials, and so on. And so ACE potentials builds on that already. And it extends the functions that are defined there. Okay, so let's just run this for now. So there was a question here that was about correlation order, I think. Is that right? Did I answer it or?
No.
No, then ask it again.
I want to see the, like which where this number corresponds to this number in the equation.
That number here?
Yeah, in the equation you
I showed on the slides. Do I have my slides up here? That's what you want to see. Yeah. So that n here, that's the correlation order, and that's what I call order in the code. And that n is exactly that, right? So because there's a central atom I and n neighbors, the body order is one more, is n plus 1. Okay? Okay, so what happened here in the meantime is we generated the model. Okay, it turns out we picked about 319 basis functions. It has a cutoff of 6.5 angstrom. That's just the default that we picked, purely empirically. Then a data set was loaded, so then it's sort of just finishing, or it has finished the assembly of the least square system in 40 seconds on 82,000 observations. That's not terrible. It then does a Bayesian linear regression. That just happens to be one of the more robust ways we found to estimate parameters. And then you can see here the error tables. This is the error tables on the test set, not on the training set. Okay, so we reach 0.5 millieV per atom accuracy on the energies and 0.014 eV per angstrom on the forces. That's quite decent. I think there are a few applications where you want to go beyond that. It's a simple data set, so it's not that hard to achieve this, but still, it's good. Okay, so now there are basically two things I quickly want to show: how to link in with geometry optimization, how to link in with molecular dynamics. So for both of these tasks, you need to be able to evaluate energies and forces, and depending on context, also virials. All of that is defined in, where are we? Sorry. In Atom's calculators, and supposedly made easier to implement using Atom's calculator utility. So these are the two packages that we use to implement potential energy, forces, and virials. So then in geometry optimization, so Michael this morning showed a package called geometry optimization that is supposed to become the official geometry optimization package. But at some point, I really desperately needed some functionality, and so I hacked something together for myself to get it to work. Everything that's in here will move eventually to geometry optimization.jl. For now, I'm using this package because it was easier to put things together. Because of that, I need sort of a little hack here also to convert systems in between different formats, which you can pretty much ignore for now. Okay, so what do I start with? I generate a copper unit cell, and then I optimize the geometry for that cell. And so what you see here is a flag variable cell is true. That means I'm not just optimizing the positions of the atoms, I'm also optimizing the cell shape. And that actually was exactly what wasn't available in geometry optimization back then. So we'll need to import the packages first. I forgot to do this. All right. But here you can see the ASE history, by the way. That's very much that notation again. All right. So now I compute the energy per atom for that unit cell. Right, so that's the prediction made by the ACE potential. That geometry optimization was performed with the ACE potential that we fitted. In the background, this uses, what is this using? Optim.jl, for those of you who know that package. So then what I want to do is I want to use that equilibrated unit cell to generate a larger cell. Right? So I take the equilibrated unit cell and I multiply it in each coordinate direction. And then delete one atom. That generates a very simple defect, right? Simplest possible defect. That's easy to equilibrate. I just didn't want to take any risk that the geometry optimization might fail. Right? So then I use again the geomopt.minimize to optimize the geometry of the defect. Now with variable cell false. Now I'm freezing the cell shape and only optimizing the positions. That converges within just a few iterations. That is such a weak defect in a way. And then I can, if I want to compute that, the formation energy for that defect. Again, every single calculation here, all the force energy calculations were done with the ACE potential. And so then comes one thing, an example I just put in this morning, because it occurred to me I should do that, where Julia actually shines, which is, I thought, okay, why don't I add vibrational entropy to this calculation? Okay, now I need a Hessian, why not? Right? So how do you compute a Hessian in Julia? You use forward diff. Because I already have the gradient. My gradients are hand-coded pullbacks on the energy. The gradients are fast. The forces are about a factor 2.5 slower only than the energies. because I have fast forces, doing a single Jacobian on the forces gives me the Hessian. This is done, and all of this is done with a few lines of patching ace potentials together with atoms, calculators, utilities. And so with that you can compute Hessians, spectrum. Once you have the spectrum, you can then compute the vibration entropy. And basically the only thing I had to make sure of is that the code,
Okay, I got this too, that makes me feel better.
Did anybody else get that?
Yeah, I did.
I just fixed that earlier, and why is this not fixed?
So you need to have the 0.1.15 version of Atoms calculators utility.
Exactly, but I thought that's exactly what I fixed earlier.
So those of you who have the error don't have the new version.
Okay.
So what happened here? This should have worked. Sorry about this.
No, so basically what happens is that the new version wants to have the chunk splitters version 3, and Atoms ace potential want to have version 2.
All right.
So that's why you cannot get the correct version.
You'll get a patch 10 minutes after the tutorial is done. We could quickly do it probably if we just develop.
Well, I can do the patch while you are going on.
Let's not worry about it. I think the main point is that things like that are really easy to do in this context. Where should I be now? I think I've lost my tutorial. Okay, so the last part now. If you want to run molecular dynamics simulation with these ace potentials, obviously no problem, right? So here again, I'm just generating a bulk copper system again. I'm perturbing the atom positions a bit. I'm creating, and then I'm converting that system and the calculator basically into Molly format. I generate random velocities at a specific temperature, adding the loggers. Then I do a velocity relay integration with a thermostat, simulate for 1,000 time steps. And essentially, you should be able to use ace potentials without doing anything differently as if you were using one of the potentials that Molly provides internally. So this is where the Atoms calculators interface has helped hugely. You do this with zero effort. So that part of the tutorial was really just to show that all of this interoperability should just work seamlessly with hopefully no further hiccups. We'll see in a moment. Okay, so you can see stable temperature and stable energies, and that's all I really wanted to see. The simulation has no meaning other than to show that it runs. All right. Anything else on interoperability that I should be talking about? Any questions about it? Yeah.
How do you know what DT to use, or you just kind of?
How did I know?
What time step to use in the velocity version?
Here? Somebody who knows what they're doing told me. No, 1 femtosecond is what you always use as a default time step unless it fails, then you do something else.
So as a rule of thumb, if you have hydrogen in the system, then you need to have a 0.5. Otherwise, you can use 1 point.
And you know, this is a huge problem when you have expensive potentials and want to, I don't know, for a very, very long time. And another discussion to have.
Yeah, I think the rule of thumb should also include if you're a biologist and you need a millisecond and then you use 0.3, then you use 3. Just as a
Okay. In this case, because we have a copper, then you can use 2 femtoseconds or even 3 probably.
I mean, basically, you have to know the fastest motion of the system. Probably once the hydrogen is they vibrate harmonically on the femtosecond time scale, so you can't get any harder than a femtosecond. Because hydrogen's so light. So you basically have to have knowledge of what the fastest motion is in your system.
I think the main message here is we've been trying over the past few years to set up a little bit of an ecosystem, how to communicate between different packages that actually don't really know about one another. And so far it looks, I wouldn't say it's mature, but it's starting to come together, it's starting to work, it's starting to become usable. It makes me happy. Yeah.
Just a quick question, like, how are the self-interaction terms accounted for the machine matrix?
I'm sorry, I can barely hear.
How are the self-interaction terms accounted in the Hessian matrix? Like, when you calculate the second derivative, like, with respect to a specific atom, the corresponding potential energy is 0, right? Like, so when you do a differentiation with respect to that, do you have like a...
Okay, I need to clarify something. Self-interaction means different things to different people. What do you mean by self-interaction?
Atom with respect to itself, when you calculate the potential energy of the system, like if you pick a central atom and then if you pick the neighbors, I'm just thinking the potential energy matrix could be an atom with respect to itself accounts for 0.
Maybe it would be useful to come back to this here.
You mean the diagonal of the Hessian?
Yeah, exactly, yeah.
This is my model, okay? Here, the input into total energy are the positions of all the atoms. Hessian is a well-defined analytic operation. Self-interactions or no self-interactions.
Okay. Oh, so it's always like I with respect to the corresponding neighbors, not with I with respect to I.
You simply take second partial derivatives. It's the matrix of second partial derivatives of this expression. And how you evaluate that is another story, right? There's a lot of algorithmic stuff behind that. But at the end of the day, it's a sequence of tensor operations. And you can propagate derivatives through these very easily. I'm answering your question.
Is your question about the physical interpretation of the diagonal terms, or something specific to how it's actually computed? I think I wasn't entirely clear if it was sort of a physical question or a numerical question.
Yeah, so I initially started with a numerical question because I thought it could be really like an impact of R, like R, for example, if you take a simple LJ potential, then R respect will be really close to 0 when you divide by certain terms. Then could be a numerical issue arising from that for the diagonal terms. So
if atoms collide, you get numerical issues,
exactly,
yes.
Yeah.
But that's not self-interaction. That's just your configuration approaches the singularity in the potential energy. Then energy blows up, forces blow up, Hessian blows up. So you're not supposed to really do that in molecular dynamics.
Okay. I just saw maybe you can discuss it more later on. Yeah.
I think the term that you're talking about, you can think of it as proportional to the derivative of the force on atom I with respect to the position of atom I. And so there's lots of things happening, but it's a well-defined derivative.
Yeah. So unless you get collision, all of these derivatives are perfectly well defined. All right, so what we thought we'd do for the last part, we still have a few minutes left, is that we wanted to show you something that you cannot do in Julia yet. Basically, where is this field now really? Machine learning potentials, where has this come in the last few years, which is reasonably impressive. And maybe that motivates some people to help out.
So I have a couple of things. Including a few examples and at the end, some like looking ahead. I wanted to give a few of my own acknowledgements. So I did all of this work while I was in the UK, sort of based in the material science department with Chris Picard, and then also with Gabor Chani. And then here's the ACE Potentials sort of team. So there's a lot of people, like Cass van der Oort and Elena Vision did a lot of work. This is here just because I think it's sort of funny. Maybe some of you were at the Psy-K meeting where Gabor gave a plenary talk, so one of the big talks with this sort of provocative title, The End of Ab Initio MD. I wanted him to call it Ab Initio MD is Dead, Long Live Ab Initio MD, because from my point of view, it's not so much that these potentials are replacing DFT, it's that they're allowing you to do DFT, homology, molecular dynamics, and other things by a clever interpolation. And if you are able to do MD on large systems much more quickly, it's much easier to do things like look at cracking in silicon, where you have long, sort of maybe long-range elastic strain fields or other types of phenomena. So you need a lot of atoms, but also you need some quantum mechanics so that you get the bond breaking correct. And so one of the first successes of the gap paper, the silicon gap paper that we keep coming back to, was cracking in silicon, and we were able to reproduce it using an ACE potential. Christoph already showed this hyperactive learning workflow, and I mentioned it in the tutorial, but I just wanted to highlight one thing, which was that getting the melting point of this silicon aluminum 10 alloy, I think it's called, required only 22 DFT calculations using the sort of active learning that you saw in the tutorial, which I think is kind of neat. Okay, so now towards question of what can't our package do and what we might like it to be able to do. So here is a version of the cluster expansion slide that Christoph showed, where in red I have highlighted indices associated with the chemical species. So you start off with one, call this the A basis, the sort of one body basis, where you do a pooling operation and you sum over all the terms in the environment, and you have a different channel for each chemical element. And then once you start doing these correlation terms, so A and then A times A and A times A times A, you have in this tensor product lots of red, lots of black indices too, but lots of red indices that correspond to lots of different interactions between different chemical species. And this quickly becomes unwieldy if you want to do more than a handful of elements. Particularly if you might want to do a potential for the entire periodic table, because then you have something on the order of 100 times 100 times 100. So one big community effort over the past couple of years has been taming this species explosion. One of the earlier successes, there are a couple of different things, but one of the cute examples that's in the literature is you can think of, instead of having each individual element of the periodic table having its own channel, you can start to sort of squint and say, well, the periodic table is really only 3-dimensional, maybe 4-dimensional, and maybe we don't actually need 100 dimensions to represent species. And so this paper from the Chariati group sort of talks about these pseudo-elements, earth, wind, and fire type linear combinations of real elements. You embed your 100-dimensional space of elements into a smaller fixed-dimensional space, and they show that actually, in a similar way to the fact that the periodic table, doesn't necessarily has this 3 or 4 dimensionality, you're actually able to recover a lot of the information with the embedding of that size, of that dimensionality. These ideas are expressed in a slightly different way with some tweaks in a nice paper by James Darby and Gabor's group, Christoph as well, where they take a more mathematical, so that this picture is kind of intuitive, and then there's a more mathematical expression of some of these ideas as tensor factorizations or tensor reductions. So I recommend this if you want to understand a little bit more about how the species problem is tamed. buzzword that you might have heard is sort of message passing or graph neural networks. So the basic idea here is, rather than making an ACE descriptor that has twice the cutoff, so you're looking pretty far out away from your central atom, maybe you use a smaller cutoff, but then take this environment, the information of that environment is expressed in the ACE descriptor, you kind of condense it down to some compact form and pass that information to a neighboring atom. So now, my site energy on this yellow atom might depend on the locations and types of the nearest neighbors, but also some information about the environment of neighbors that are kind of a little bit further away, rather than just their positions. We use a little bit more of their environment. These ideas are used by lots of different groups, but in my collaborators have mostly been Gabor's group and Christoph, and so they have a MACE architecture where the M sort of confusingly stands for multi or maybe nothing at all. Uses ACE descriptors in a sort of smaller sphere, condenses that information, passes messages around. Achieve a few different things, more accuracy. Also, it is a deep learning model with some of the tensor reduction features that I was mentioning, so it's able to tame the species problem as well. It's hard to kind of pull these models apart and say, this is the feature that makes it expressive, this is the feature. There's a lot happening simultaneously. But the state of the art is probably something like this. Most of these models are not implemented in Julia. You tend to have people working in PyTorch or JAX or and then in the same way, exporting to LAMPS or LAMPS with Cocos for GPU simulations. So a lot of the back-end sort of refactoring that I mentioned that Christoph and his team have done will make things like this easier. I don't know that the plan is to do exactly this kind of thing, but the hope is to sort of be able to have more expressive models if we decide we really want them. Probably you've seen lots of splashy press releases from, I don't know, lots of different groups. So Google has a foundation model for materials chemistry. Microsoft does. There's a meta one that came out last week or something. But using the same ideas that we've been talking about today, mix in with some of these other features, tensor factorizations. Our team was able to make a MACE model trained on the materials project that is kind of remarkably stable and a good starting point for if you have a new problem and you just want to do a quick MD run to see, learn something quickly. You maybe won't get a quantitative answer, but you'll see a smooth trajectory and maybe get some data that you can then run DFT on to get relevant configs for a fine-tuning of this model. You might try this MACE MP0. Things that we might, as the Julia community, think about over the next couple of years. Thanks very much, and we'll happily take any further.